Hi there, this is Professor Myers, formerly Professor Gracie. I work at Miracosta College, and today I'll be teaching you about the disc method and the washer method. So we're going to be taking a look, extending ideas from 7.1. I'm working out of the Larson text, and we are extending ideas from the area between curves to what would happen if we rotated one of those regions about a horizontal or vertical line, right? So here we go. We also will be looking at finding the volume of a solid that has known cross sections. So that'll be coming up as well. Alrighty. So the disk method, it's really pretty cool, and sometimes people find it a bit hard to visualize, but there's a ton of applets online that you could look at. So sorry, there's a few typos and formatting things that were going on. I'm not quite sure what was happening, but just bear with me. The content should be good. All right, so this should be region. When a region in the plane is revolved about a line, the resulting solid is called a solid of revolution because it was made by revolving about an axis. And the line that it's revolved about is called the axis of revolution. And it doesn't have to be the y or the x axis. Sometimes it is, sometimes it isn't. Just needs to be a horizontal or vertical line. Right? So you've seen these in life all the time. Axles, bottles, funnels, bowls, anything like that is an example of something that we'd be able to find the volume of today after the lesson. But we're going to just take a look initially at, okay, what's happening with the volume of a disc. So think about like a CD, real thin disc is a CD, if you guys even know what those are anymore. All right, so here we go. Here we go. If you have let's say that we have some sort of axis that we're revolving about. So this axis is our axis of revolution. So we have a horizontal axis of revolution. And what's going to happen is you're going to have your representative rectangle, just like you've had before with the area between curves. So this here is your representative rectangle. And if you think about this, you've got the width of the rectangle or the base, and here you've got the height of the rectangle, but we like to call this R, okay, for radius. So what ends up happening, so this part is our axis of revolution. So imagine what would happen if we were to revolve this guy across this axis. So what would happen is we'd have something like this. So here's our axis of revolution. Here's the representative rectangle. Actually, this is the whole thing for this example. And remember, we were revolving about this axis here. So what'll happen is you'll kind of get this sort of like little shadow rectangle, right? That's going to reflect across that axis. And you just kind of need to visualize what happens as you flip that thing about like a gymnast on the bars. You're flipping this across the axis, and it rotates, and you end up with a circular cross section, right? A circular cross section. Whoops, let me do that better. So, all right. you'd end up with a circular cross section. Cool so far? And you know what? Every time I try to shade these things, it ends up being kind of a disaster. So hopefully you can kind of visualize this here. So what we'll have then is we'll have this disc, okay, this disc that we're working with. And do you guys remember the volume of a right circular cylinder? Good. So volume of a right circular cylinder is basically the volume equals the area of the base, which is pi r squared, times the height. Okay, so far? So now in our picture here, okay, the height is actually going to be, the height of the rectangle is really represented, if you can kind of visualize that this is a cylinder lying on its side, so a short little Coke can lying on its side. So actually the height measure is here. That's our height measure. And what we call that height measure is the change in x in this case from this orientation, right? That's our height measure. Now, if you take a look over here at this measure right here, that actually happens to be our radius. Now, when we're speaking of the disc, and you'll see why we do this soon, but when we're speaking of the disc, we call this capital R, and it's in terms of x with this orientation. So this is what we've got. So what happens is you've got these cylinders. Now in this case we have a single cylinder, but let's just imagine, you know, like a snowman, right? If you wanted to figure, right now it's Christmas time, so if you wanted to figure out, you know, the volume of a snowman, then it would be the volume of a series of spheres, right? And these spheres could all be chopped into these right circular cylinders. So the idea is you sum infinitely many of the volumes of these right circular cylinders and you'll get the overall volume. So in terms of calculus, what happens is you end up getting your delta V is equal to pi r squared delta x, right? And if you think about approximating the volume of a solid using, this should be lowercase, sorry, using n discs of width delta x and radius r at xi squared, and it's actually going to be r at xi squared, it gives us this summation. But what do we know about summations? We know that as the norm of delta, which is the width of the largest subinterval, approaches 0, then the number of subintervals approaches infinity, right? So what we have is our definite integral, and at the end of the day, the volume of a solid of revolution is this formula here. And that is if you are rotating about a horizontal axis. We'll do the formulas soon of what would happen if you were if you were revolving about a vertical axis. Okay, so here we go. Now, if you think about what we've got going on, let's see what we've got here. Actually, write some more stuff here. So if you think about what we've got going on, you're basically taking the volume of a disk, a pre-calculus formula, and then you are applying what would happen at the ith interval in a summation, and then you end up getting your definite integral to, at the end of the day, give us a volume formula of pi times the integral from a to b of capital R at x squared dx. And then let's take a look at an example. Okay, so for example 1, what we have is we've got our region is enclosed by below the graph of x squared on 0, 1, and it's revolved about the x-axis. And this one needs a few more bounds. Let's fix this up a little. Sorry, somebody else had done this one. Okay, so the region under the graph of, let's say, y equals x squared, and then the line y equals 0, which is the x-axis, and it's from 0 to 1 about x. So we're good there. So let's take a look at that picture. So we have this picture here. And our order pairs will have 0, 0, and 1, 1. So this is 1, 1. Let's do our -1. So our graph of our region is going to be, we'll have a point at 0, 0, at 0, 0, and we'll have an ordered pair at 1, 1. And let's see, at 1/2 we'd be at 1/4. So about here. So it's going to look something like this. And then we've got the bound going down at x is 1 and x is 0. So our region that we're revolving looks like this. Got it highlighted in the blue. And you guys were used to doing that when you were working on the area between curves. Now, what you want to look at here is our representative rectangle for the region. Okay. Now, in the disk and washer method, your rectangle is always going to be perpendicular to your axis of rotation. So we're rotating about the x-axis. Okay, and what will happen is we've got our representative rectangle, and what we have is this little length here, right? This teeny, is there a smaller one? This little tiny length right there is going to be, do you remember what that was? It's going to be our dx. And then this length here is going to be our capital R in terms of x. And can anyone tell me what that is? Beautiful. It's just equal to x squared. So, in general, our volume is equal to pi times the integral from a to b of capital R at x squared with respect to x. And putting in the information from our problem, we'll have the volume as pi from 0 to 1 because it's about x, and we're going to have x squared squared with respect to x. So then our volume is pi times the integral from 0 to 1 of x to the 4th dx, which gives us the volume is pi times 1/5 times x to the 5th, evaluated from x equals 0 to x equals 1. So we'll get pi over 5 times 1 to the 5th minus 0 to the 5th, which is pi over 5 of a cubic unit. Okay, so that one wasn't so bad. Now let's think about this. If we thought about rotating this same region about the y-axis, would it look the same? I mean, right now what's happening, sorry, I forgot to fill this out for you. Right now, basically what's happening with this guy is you got a region that looks like this. So your kind of ghost region is like this. And so then you end up getting something, a solid of revolution that's going to look like this. So you get this whole business, right? And that's your solid. So it looks almost kind of like a horn, doesn't it? Or something like that. Now visualize what would it look like if you rotated about the y-axis. I mean, it would be a lot different, wouldn't it? This is your x and this is your y. So let's check it out. Why not? Right? We can do this. So considering the same region, all right, so let's now consider the region bounded by y equals x squared, y equals 0, on revolve this about the x-axis, the y-axis. Okay, so now our picture will look more like this. We'll have our x and our y. And our region will be a little bit different this time since I changed the bounds. I've got a bound here, and then I've got a bound from that curve, that conic. Okay. And let's see. think we'll be good there. And so what'll happen is our region is going to be, well, let's back up a little bit. Do you see that if we're going to be rotating about the y-axis, our representative rectangle is going to be perpendicular to that axis, the y-axis. So it's going to be sideways, right? So that means that this little bit here is going to be dy, and this here is going to be capital R of y. So let's get these in terms of y. Notice we're in the positive part for the x's only. So here, if you take a look at y is x squared, we can write that as x is the plus or minus the square root of y, but we're only considering the positive root because the x values are all to the right of 0. And x is 0 is fine, it's another bound. But now, so that was this stuff. This here means that 0 was less than x was less than y, or 1 rather. So if you plug those values in, do you see for y, do you see you'll get 0 is less than y is less than 1? Good. So we will end up having a region that looks somewhat like this. So you end up getting something that's going to look more like a bowl. Okay. But actually it's all filled in, there's no hole in it. So I guess a better thing, better visualization would be like I don't know, a full cup or something, a full bowl, right? Or an upside down paperweight, something like that. All right, so anyway, here's what we've got going on. What is our capital R of y? Good, it's equal to root y. So what will happen is our volume will be equal to pi. Now we've got to be careful of our limits of integration. We have a function of y, so our limits need to be about y. So in this case they don't change, but it's y is going from 0 to up to 1, right, up to 1. So this here is what y is going to, all right? So we'll have root y squared dy. So then our volume will be pi times the integral from 0 to 1 of y dy, and we'll have pi over 2 times y squared evaluated from 0 to 1, and we'll get pi over 2 times 1 squared minus 0 squared, which gives us, good, pi over 2 of a square, actually square units I guess, yep, square units. And that's our result for this guy. So in general, right, what will happen is we'll have this going on. We'll end up having, if we have a horizontal axis of revolution, right, so I'll just come up here a little bit. A horizontal axis of revolution would mean that you would have your, let's do like this, your representative rectangle is going to look like this. Okay, so that's going to be your capital R of x, and right here is going to be your dx, and your axis of revolution is going to be horizontal, right? So when you have this horizontal axis, of revolution, what happens is you get your volume V is equal to pi times the integral from a to b of capital R at x squared dx. Now, if you're thinking of a vertical axis of revolution, your representative rectangle will be perpendicular, and so this little piece is going to be dy, and this here is capital R of y. So your formula changes a little bit. You end up, for your vertical axis of revolution, you get the volume is equal to, so instead of going from A to B, they write it as C to D so you don't get confused. And then you have your capital R of y being squared, and then you have dy. Okay, so now let's take a look at the waasher method, right? So with the waasher method, basically what's happening is there ends up being sort of a hole in the middle. So you end up having two radii. One's considered the inner and one's considered the outer, all right? So if you have your, you know, a rectangle inside here, so let's say you've got, I don't know, let's just say it's a horizontal axis of revolution. And suppose that instead of being right on that axis, right, your representative rectangle ends up being here. Actually, let's do this differently. Let's just do, we'll do the representative rectangle, that's fine. So your representative rectangle was kind of floating. So what happens is you end up having these two radii. So here, this ends up being your big R of x, your capital R of x. And so you basically consider, okay, if I found that entire area as if my rectangle was resting on the axis of revolution, what would I get? And from that, you subtract out this little bit, which is R of x, and that subtracts out the volume. I think I said area before, sorry. That subtracts out the volume that was overcounted, all right? So what ends up happening is you have these two separate volumes that are being subtracted from each other. So you end up getting this formula, all right? So let's go ahead, let's see what I have in store. My evil plan. Okay, let's go ahead and do, I'm going to just make up an example here so we can use this formula right off. Let's go ahead, this is one of my favorite problems, and we'll put in a little example here. Bonus example. And we want to find the volume of the solid formed by revolving the region bounded by the graphs of y equals the square root of x and y equals x squared we revolve it about the x-axis. Okay? So let's check out what this looks like. You've got these two different graphs, right? We'll do this one in blue and we'll do this guy in green. So if we go here, and we're revolving about the x-axis, so I'm going to leave room below. And first of all, I mean, where the heck do these graphs intersect? So let's remember how when you're finding the area between curves, if you're not given any kind of bounds about x, you have to solve for those bounds. So here, do you see that if we looked at set them equal to each other, so we set root x equal to x squared, right? And if we were to square both sides, we would get x is equal to x to the fourth. So then, bringing that x to the other side, we get 0 is x to the fourth minus x. Factoring out an x, we get x times x cubed minus 1. So x is 0, or x cubed minus 1 is 0, which would give us x cubed is 1, which gives us x is equal to 1. So we know that our bounds about x will go from 0 to 1. And if I plug in a 0, I get an output of 0 on either graph. And if I plug in a 1, I get an output of 1 on either graph. Okay, so let's take a look. So the blue graph is going to, of course, have ordered pairs at 0, 0, and 1, 1. Now, if we look at 1/4, an input of 1/4, we'll get an output of a half. So it's going to go something like this. And then our other graph, which was y equals x squared, sorry, it's going to make sure that's on the line. All right, so again, 0, 0, and 1, 1 are on that graph. But now if we're at 1/2 input, we'd get a 1/4 input out. So it's going to go something like this. So our region that's being rotated, okay, is this region here. It's bounded by these guys. Okay. So basically what's going to happen is this. I know they like to do the whole representative rectangle thing, but I kind of take a little bit different approach. For the first volume, what's going to happen is your representative rectangle would look sort of like this. It would go all the way down. Do you see that? And then for the smaller one, it would go from here at any given time down. Actually, you know what? I'm going to move that over so you can see it better. Okay, so if you consider coming here, okay, this rectangle, when revolved, gives you too much volume, doesn't it? So this right here, this whole thing, is capital R at X. Now, this piece of it here, right, is little r of x, because that's the part we're going to end up subtracting out. And then what's inside the region is the representative rectangle for that. So this shape is going to look something like this. We'll have something like that. And so then when it revolves about, it's going, do you see how it's going to have this hole in the middle now? So it'll go something like this, and it's got that hole in the middle of the plate. So it's really kind of groovy. So you'd end up with this here, right? And then there'd be that hole in the middle there. Okay, so what'll happen is let's kind of label everything now. Go down here. So remember that so our capital R of x is going to equal to what? The blue graph, right? And the blue graph was root x. And our little r at x is going to equal to, beautiful, x squared. Okay? So what will happen is our volume will be pi times the integral from, good, we were going from 0 to 1, I think. And it's going to be capital R at x squared minus little r at x, the quantity squared, with respect to x. So plugging in those things, we will have, actually let's do this in general, it would have been the integral from a to b. So now our a is 0 and our b is 1. And then we'll have root x squared minus x squared squared, all with respect to x. So then our volume will be pi times the integral from 0 to 1 of x minus x to the 4th with respect to x, which will give us, the volume is pi times 1/2 x squared minus 1/5 x to the 5th, evaluated from x is 0 to x is 1. So then we'll get our volume is pi times 1/2 times 1 squared minus 1/5 times 1 to the 5th. And do you see that the lower limit of integration, they're all going to zero out in this case? So we'll have the volume is pi times 5 minus 2 all over 10. So we get our volume is 3 pi over 10 cubic unit. Okay? All right, so then here's another example. Okay, let's look at this guy here. We want to find, we've got a couple different problems here. We want to find the volume of the solid generated by revolving the region bounded by the graphs of y is 2x squared, y is 0, and x equals 2, about first the y-axis and then the line y equals 8. So let's check out what we have. So for part A, we have something like this, our x and our y. And if I plug in a 2 for x, I'm going to get out 8. So my initial graph, I have an ordered pair at 2, 8, at 0, 0, and at 1, 2. So it's going to look like this. And then I have this other bound at x is 2. I am rotating about the y-axis. My region will look like this. Okay, so now remember that we are rotating about that y-axis, so we have to be vertical to that. So if you think about, a rectangle at any given time, what will happen is we'll have this whole thing, do you see, is going to yield the larger volume. So that's going to be, this will be dy, this will be capital R of y, and then from here to here will be our little r of y. So let's see what this guy is going to look like. It's going to look like so it'll go something like this. And so it'll have that hole in the middle. So it would be hard to see, but you'll have this hole in the middle. So we've got this whole region going right here. So kind of like a box with a scoop dug out or something. Maybe something for packing a Christmas ornament or something. All right, so here we go. What did we find? Our capital R of y, what are we going to have to do? Everything is in terms of y equals some function of x, right? So here, if we take y is equal to 2x squared and we isolate x, do you see we'll have y divided by 2 equals x squared. Now our initial blue region, it's all to the right of 0, so we'll just do the positive root of y over 2 is equal to our x. Good so far? So now that one is going to be which one? Capital R of y or small r of y? Beautiful. It's going to be our small r of y. So r of y, little r of y, is equal to the square root of y over 2. Now, let's take a look at the other one, x is 2. That one's pretty easy to see that that will be our capital R of y is 2. So you've got this whole cylinder with a radius of 2, and you're subtracting out from that a cylinder with radius of root y over 2. Good so far? Beautiful. So now we'll do our volume. So the volume in general is the integral from c to d this time because it's about y. And then you have your pi, and then we have our capital R at y squared minus little r at y squared, all with respect to y. So in this case, we'll have our volume equals pi. Now y is going from where to where? Beautiful. It's going from 0 to 8. And then we'll put in our capital R of y was 2. be squared. And then our little r of y was the square root of y over 2, and that's going to be squared with respect to y. So we'll get our volume is pi times the integral from 0 to 8 of 4 minus y over 2 with respect to y. And then we'll have the volume is pi times 4y minus, it'll end up being y squared over 4, and we're evaluating that from y is 0 to y is 8. So we'll get the volume is pi times 4 times 8 minus 8 squared over 4. And then do you see the lower limit of integration is just going to end up being 0? Good. So we will have our volume is pi times, we'll have 32 minus 64/4, which is 16. So we'll get 16 pi cubic units. And we're done. How'd you do? Awesome. Okay, so now let's look at this other case. The other case, if you recall, was we're going to be now going across, rotating about the horizontal line y equals 8. So now we'll be back in terms of x for everything. So our picture is going to look like something like this. So actually, we're going to need this to be down. Okay. So if we're rotating about the line y is 8, and then we'll have to be up here at 16, so 9, 11, 12, 13, 14, 15, 16. And so now that line y is 8 is our axis of revolution. Put that in green. And we'll have our picture of our graph from before. So x. So we're going to have an ordered pair at 2, 8, at 1, 2, and 0, 0. Oops, blue. And we're also bound here and here. So our rectangle, we could picture it kind of like this. It's not really the representative rectangle, but so here, what is this guy? Beautiful. This is our capital R of X. And what is our capital R of X? Awesome, 8, right? And then here is our little r of X. So our little r of x, what is that going to be? Topmost graph is beautiful, 8, and then minus the lower graph would end up being awesome, 2x squared. Okay. So now our volume, and what are our limits of integration? A will be good, 0, and B will be 2 because we are going in terms of x. So our volume will be pi integral a to b of capital R of x squared minus little r of x squared dx. And our volume will be integral from 0 to 2 of 8 squared minus 8 minus 2x squared with respect to x. So crunching that out a bit, we'll have the integral from 0 to 2 of 64 minus 64. Let's see, it'll be minus a 64. That would have been a minus 32x squared, so it'll turn to a plus 32x squared. And then we'll have a minus 4x to the fourth dx. So that simplifies a little bit, right? The 64 is 0 out, so we'll end up, oh, I forgot my pi, sorry, on these two. So we'll have pi times the integral from 0 to 2 of 32x squared minus 4x to the fourth with respect to x. So integrating, we will get 32 thirds x cubed minus 4/5 x to the fourth evaluated from 0 to 2. So our volume will be pi times 32 times 2 cubed over 3 minus 4 times 2 to the fourth over 5. And do you see that the lower limits will just be 0? Good. Okay. So we will get the volume is pi times, so 8 times 32 will be 256 thirds. And then minus, we'll have 16 times 4 is 64, and that'll be over 5. So continuing, we will have our volume is pi times, getting a common denominator, we will have, let's see, it'll be over 15. So we'll have to multiply 256 by 5. So we'll get 1280, and then we'll be multiplying 64 by 3, so that'll be 192. So we will get 1,088, if I did it right, over 15 pi. And that's in cubic units. Okay? All right, so see, they're very different depending what, the shapes are very different. Oh, so just let's finish up what it would look like. So you'd end up over here, it would reflect like this, this guy. And then it would go something like this. Right? So your region would look like this. And then it would have revolved, so it would be circular like this. So your whole, the outside of your volume would look something like this. There'd be that hole in the middle. Groovy? Awesome. Alrighty, so next there's a part about looking at solids with known cross sections. Alright, so on this one, given the amount of time that we've spent on the lecture, I think what we're going to do is we'll look at the first problem on here, but not the second one. So here we go, volumes of solids with known cross sections. So basically, if you've got, let's see if this printed at all. Okay, so if you've got so if you've got a cross section that is perpendicular to the x-axis, then what you'll have is something like this. So if you think about, try to make a good visual for you, but if you think about this being x, and this being y, and you've got z up here, right? And suppose you had, I don't know, you had a visual where you had all your cross sections were perpendicular to the x-axis. Okay. I'm going to do just a real simple sketch here, so I don't ruin the whole thing here. So basically, any cross section, okay, and this guy is perpendicular to our, let me do this somewhere else. Any of these cross sections are going to be perpendicular to the x-axis. Okay, so this is kind of like a cross section. I know, very simple. There's a really good visual in your book. So what's going to happen is this right here is going to be your delta x, okay? And what you'll have is you'll have x going from, so this would be, x equal to a to x equal to b. And this cross section has an area for its, so you're considering the area, basically the area of any of these sections in there, and then times the height, if you will, which is our dx. So what happens is, for this particular situation, when you're perpendicular to the, so you're perpendicular to the x-axis, what'll happen is the volume will equal the integral from a to b of capital A at x times dx, right? And so for this one, you know, your area is a square, right? So you'd be multiplying the areas of those squares times the height, really, is what you're after. So similarly, it's a little different. I'm not going to make the picture for this one. If you go perpendicular to the y-axis, your formula will change. You'll have the volume is the integral from C to D of your area in terms of y with respect to y. Okay? So, let's take a look at this problem here. Okay? It's kind of a really awesome problem. I know I'm a dork, but I think it's super awesome. Here we go. We want to use the disk method to verify that the volume of a right circular cone is 1/3 pi r squared h, where r is the radius of the base and h is the height. So let's take a look at a picture. Okay. So we can do something like this. This is x, this is y. And your graph, if you remember correctly, you would have something like, oops, do this right. So 1, 2, 3, 1, 2, 3. So you'll have the line y is x going on. And you would do this until you get to your height, okay, your height. So you'd have your height, would be over here. So that would be like your x equals h. And this one, then, if you think about it, you'd end up having, you know, your kind of reflection here. And then when you revolve it, you'll get your cone. So our height is kind of on its side in this case. So now here, let's take a look at what we have going on. So do you guys remember that there's a relationship between any triangle? Basically, you make similar triangles in the cross section. So if you just kind of consider your cross section here, right? And let's just say we called this R prime, right? And what would this measure be right here? I mean, the whole measure would be h, right? And this little bit would end up being h minus whatever x you're on. Does that make sense? Okay, so now if you made this proportion, we would get r prime is to this r right here r as h minus x is to h. So you're looking here, that's h. All right? And they're similar triangles. So isolating for r prime, do you see you would get r times h minus x divided by h. Now let's talk about what is the volume of a cone. What is the volume of a, or not the volume of a cone, I'm sorry. It's really late. Let's think about what is the area of this cross section here. So we want to figure out the area. So if we looked at this guy, do you see it would be a circle? Can you visualize that? And so this known cross section here, right, where our with a radius of r prime is a circle, right? So you'd end up with your area in terms of x is going to equal to pi times r prime squared. And this in turn is equal to pi times, good, r times h minus x over h, all of that squared. So a of x would be pi times r squared times h minus x, the quantity squared, all over h squared. All right, so far? Very good. So now let's take a look at what we have. So the volume is going to equal to the integral. So we're going from x equals, good, 0, right? Well, let's do this in general. So from a to b, our area of x dx. So our volume is going to go from 0 to, beautiful, h. And our a of x is pi r squared over h squared times, I'm going to expand that square, so we'll have h squared minus 2 times h plus x squared with respect to x. Now we're integrating with respect to x, so everything else we could treat as a constant that is a multiplier here. So the pi r squared over h squared we can take out, and then we'll have the integral from 0 to h of h squared minus 2xh plus x squared with respect to x. Okay, so continuing, we will have our volume is pi r squared over h squared times h squared x minus, the 2's will divide out, so you'll have x squared times h plus 1/3 x cubed evaluated from x is 0 to x is h. And this will give us, our volume is pi r squared over h squared times h squared times h minus h squared times h, and then plus 1/3 times h cubed And then the lower limit will just zero out. So our volume will be pi r squared over h squared times h cubed minus h cubed plus 1/3 h cubed, which will be, these zero out, so you're going to end up getting pi r squared over h squared times h cubed over 3. So these divide out all but one of these h's. So at the end of the day, we get 1/3 pi r squared times h. Isn't that awesome? All right. You guys have a fabulous night, and I will be talking to you soon. Bye.